The last thing we did on Friday was I defined the kernel of the action and what it meant for the action to be faithful. Let me give you a couple of examples along those lines. Example 416. So first we're going to let G act on itself by conjugation. So here, in this example, my group is G and my set is also G. And the way I want to act on some X G is GX G. Then the orbit so what's the orbit of some X and G? Well, it's this set here. I think orbit is a very good word for this. I mean, it's just take your element X and it's where it orbits. It's everywhere that the group actually can take it. This is all the conjugates of X. Notice that one example of a G and G is the identity. So certainly X is in its own orbit. That's always true for any group acting on a set. If, so let's continue this. It's a subgroup of G acting on G by conjugation. And we will say that X is in G. Then remember what this notation means. This means the stabilizer in X, or I'm sorry, the stabilizer of X in H. So this is everything in H that leaves X alone. Let me see what this looks like. This is all H and H. So H, X, H inverse is equal to X. Right? This is just everything that stabilizes X under conjugation. Another way to look at this is this set H and H. Just massaging this here a little bit. This is HX. And we actually have an old name for this. This is actually the centralizer of X in H. So it's everything in H centralizes X and the old notation X. And of course, in the case that H is G, then this is the centralizer in G of X. So let me represent again. Now, the subgroups. Okay, so what I want you to do now is I want you, my set S is the collection of all subgroups of G, and H is a subgroup of G that acts on this set by conjugation. Let me kind of clarify what this means. H acting on some subgroup, so let K be capital K be a subgroup of G. And notice that this is also some other subgroup, right? So your action does what you want it to do. It It's a map from H cross G and G. And it's pretty easy to see that this is the identity of leaves K alone, and that you get the associativity. Now, the subgroup of H, some subgroup KG, is precisely equal to okay, and let's see, I want this action fixed K, so H, K, H inverse, K. So if you collect all this, this is the normalizer of K and H. So notice in this case, it's not necessarily true that, well, so if you take H equals G, then this is the normalizer in K of G, and K is a subgroup. For this notation right here, it's not necessarily true that H is contained, it's not necessarily true that H and K are comparable. This is just a collection of everything in H that actually normalizes K. And so it will contain, for example, K intersect H. Okay. Okay, any questions on that? Okay, here's another, I've used this word a little bit before. It shows up on your homework. Let me give you the following definition. This is a rather important concept. So suppose you have G and it's acting on A. We say G acts transitively if so the action is transitive if given any pair of elements in the set you're acting on. There exists a G and G such that G acting on X. So in other words, what it needs to be transitive action is if you pick two elements out of the set at random, there's something in G that takes X to Y. And of course, by definition, vice versa. This is equivalent to saying that there's only one orbit, right? Because what that means is picking any two elements, you can operate on the first one to get the second by something in G. That means that any Y is in the orbit of X and conversely. So there's only one big orbit. So another way to look at this is this action has only one orbit. That is, all the elements in the set that you're acting on live in the same orbit. Okay. Now, let me point out that if I give you a set, yes.
So here, the existence of G is uniform or not?
What's that now?
I mean, G is depending on XY or it's uniform?
Oh, no. The G depends on the choice of X and Y. Right. So let me point out that the symmetric group Sn acts on the set 1 through n, right? And in fact, it acts transitively, doesn't it, right? Because if I pick two numbers between 1 and n, say I and j, that are different, then there's some element of Sn that takes I to j. In fact, there's a lot of it. But the easiest one I could pick is just the transposition ij, right? Everybody agree with that? Now, of course, you could have a group act on 1 through n just by having the trivial action, right? Everything goes to itself. So you could have Sn act on that in a trivial way. It's kind of stupid, but you can do it. This begs the question, okay, suppose I have a group and a set. How many ways can that group act on the set? One for sure, trivial, right? But are there others, and how can we figure this out? And we'll answer this question now. If A is set, then SA is the set of permutations of A. I'm going to use notation here. And of course, so S of A is just a collection of functions from A to itself that are bijective. So I'm going to use that notation here. I want you to be following really cool theorem, actually. Then there is a bijective correspondence between the actions of G on A between the actions of G on A. This is what we want to count, and the homomorphisms. From G into the permutations of A. So here's what we have. And I'll kind of write down how this correspondence works. So, if this bijective corresponds from actions of G on A and homomorphisms from G into the permutation. And how's this going to work? Well, suppose we got B into SA. How am I going to get an action? I need to get an action out of this. And what you got to do is you got to do what comes naturally. So somehow I want to use this. How's this action going to work? Well, right here, G acting on A. How about this? Phi of G. Now, what's phi of G? Phi of G is now a permutation of A. Oh, how about that? So, getting a homomorphism from here to here, then we have G acting on A is this thing now, it itself is a function acting on A. So this is a permutation. So this takes it to another element of A, which is good. And how do you suppose it works the other way? Although I'm just going to do this way and show that it's one-to-one and onto it. What's the sort of the inverse now, right? So given an action, G cross A into A, how do you suppose you can make a homomorphism? Well, I want to use this action to make a homomorphism. Now, this is a function, so since it's a function, I got to tell you what it does to A. I want phi of G acting on A, what do you suppose it is? So see what this is, phi of G, when you plug in A, that gives you an element of A. So you can think of phi of G now as a permutation, right? Right, so phi of G is actually this permutation of A and it goes to G. Right? So let's work this out. Let's verify if this works. Questions? Yes.
I just wanted to say the notation in the text on line has no parentheses around the A in the definition, or I guess here the orange as G follows A equals like phi of G A, and it took me a while to realize that was a
function.
A function does that.
I should probably doctor that up. Yeah, I'll fix that. Okay, so let's go through this carefully. So suppose we have a homomorphism from G into the permutation of A. Now I want to show that my rule here up here in orange actually gives an action, right? I want to show first that G acting on A given by phi of G, so it's permutation of A, is well, so let's go through it. Number one, E acting on A is phi of E of A. But what is phi of E? Well, this is a homomorphism, so this should be the identity permutation, which is A. Because remember, any homomorphism must take the identity here in G to the identity function over here, right? And so you gotta love homomorphisms. So this does what I need it to do, right? The identity leaves this alone. And two, if I look at G1, G2 acting on A, I wonder if that's the best way to do it. But anyway, this should be phi of G1, G2 applied to A. But this is a homomorphism. So this is phi G1, phi G2 applied to A. Which is check myself here. So this is right. This is phi G2 applied to A, which is G2 applied to A, and then that applied to A. So this, in fact, is an action. So what we really need to do is show that this correspondence is bijective. We need to show it's one-to-one and on. Okay. Now, 1-to-1, suppose P and pitchfork, these are both homomorphisms in the SA. Suppose they get the same actions. So what I want to do is show that Phi and pitchfork have to be the same thing. So what does it mean to give the same action? So phi of G of X and pitchfork of G of X G is in G. And this is true for all X and X. So BG and pitchfork G are the same element of SA. Because what you're saying is these two functions, these two elements of SA, no matter what X is, they've got the same destination. So these two are the same permutation. And this is true for all G and G. Therefore, the two functions are the same because they behave the same on every element of the domain. Okay. So they give part of the bijective correspondence because we know now the two different functions go to two different places over here. We need to also show that an arbitrary action can be gotten from one of these functions. So now, let's suppose G acts on that. Via some action. Now I am going to define P into SA, and I'm going to use this action to define this by P of G is so it's just a notational change. P of G is phi sub G, and let me tell you what the rule is of this. Phi sub G of A. So here's where we use our action here. Note if BG X equals BG Y, then by definition, G acting on X, G acting on Y. And now compose both sides on the left, G inverse, and I get X equals Y. Okay. And so this phi G is, phi sub G is 1 to 1. And also notice that if X is any element of A, then if I operate, or if I hit X by G inverse, then I get, well, I don't know what I get, but I get something over an A, call it Y. Therefore, so G is a permutation. So in other words, this homomorphism, this phi G you end up with, phi sub G you end up with, is an honest to goodness permutation in SA. Okay. And finally, I'll let you check this. This is P of P1, P2, P1, 2. So, P. And so there you go. It's on to as well. By the way, let me illustrate this with an example. And in fact, yeah, I want to pay attention to this here because this shows you how the correspondence works between the action and the work. Consider the group Z6, 6th group, order 6, under addition, right? I'm going to show you how the permutation representation goes. What these things act on itself by left translation? I put left in parentheses because this group is abelian and my operation is addition, right? And so let's see what happens. The element 0 induces the addition. Now, let's look at, that's no shot here. Because when I add anything here to 0, it leaves it alone. So the permutation is 0 goes to 0, 1 goes to 1. So, but what happens when I add 1? Well, now 0 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 0. Everybody see how that works? What I'm doing is I'm letting the group act on itself by adding 1. Right? So where does this go? 0 goes to 1, 1 goes to 2, and so forth. So I agree with that. What happens if I add 2? It's a little bit actually maybe more interesting. 0 goes to 2. 1 goes to 3. 2 goes to 4. 3 goes to 5. 4 goes to 0. And 5 goes to 1. let me do one more, and the rest is more obvious. Have 3, 0 goes to 3, 1 goes to 4, 2 goes to 5. 3 goes to 0, 4 goes to 1, 5 goes to 2. So the way this homomorphism will work, you correspond this action to a permutation of the elements here, right? So for example, this one, let's see what happens. The homomorphism would take the element 1 to, let's see, 0 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 4. Notice this is a 6 cycle, order 6. Forward adding 2, what permutation would it induce? We'll see 0 goes to 2, 2 goes to 4, 4 goes to 0, and then we'll say 1 goes to 3, 3 goes to 5, 5 goes to 1. Notice when you multiply this by itself, you get this. What happens here? I bet you can probably guess. 0 goes to 3, and 3 goes to 0, 1 goes to 4, 4 goes to 1, 2 goes to 5, 5 goes to 6. So basically what this particular, for this translation by the element 1, then what you get is this. So you'll get basically the powers of the 6 cycle. So basically what you've done is you've turned the additive group to 6, and when you look at it as permutation, you turn it into multiplication. Any questions? So that's basically what you do is you define the permutation by looking at the action and seeing how it moves around the elements. All right. Here's another quick example. Example. Let equal S3 and A be subgroups. Let's say and we'll say that G acts on A by conjugation. So let's actually, I'm going to number these so I can keep track of it. So I'm going to call this first group, I'm going to call it 1. And E13, I'm going to call it 2. And E23, I'm going to call it 3. Okay. So, for example, sure. Give me an element of S3. Anyone you want.
S3.
Okay, let's look at 1. Let's see what happens when we do this. When you do 1, 3, actually, if I've been smarter, I guess I'll do what's called H1, H2, H3. Do that. When I conjugate H1, O13, I get E, and then I get 1, 3, 1, 2, 1, 3. one goes to 3 back to 1, so this must be 2, 3. Okay. When I conjugate H2, 1, 3, it appears to leave things alone. And when I conjugate this. So the permutation H1 and H3 swap, and H2 is left alone, right? So you might think of this as the permutation H1, H2. Or I'm sorry, H1, H3. So it's just this permutation 1, 3, right? So 1, 3 under this homomorphism sort of goes to itself. Let's try another one. We tried an element board 2. Let's try 1 times 3. What happens here? Conjugate this way. This is E 1, 2, 3, 1, 2, 1, 2, which is E. Let's see, what does this go? 1 goes to 1, so this comes to 2. 2 goes to which is actually, this conjugates to which one? H3. And one, 3, 1, 3, 2. One goes to 2. And this is H1. And finally, 1, 2, 3, H3, 1, 3, 2. This is E, 1, 2, 3, 2, 3, 1, 3, 2, which is E. Which is H2. So this one actually goes to the permutation. Let's see, H1, H3, right, H1 to H3, H3 to H2, and H2 back to H1. Good. So this is like, this one goes to 1 through 2. So that's how you look at an action and see the permutation that it gives. Everybody, okay. And you can go through the whole list and get the homomorphism if you like. Okay. All right, here's one of my very favorite things. This is way cool. Whatever this is. 4110. Acting on S, or acting on A. And we'll say that X is an element of A. Then the orbit of X, orbit of X is the index of its stabilizer. So let me write this out more. So if you count up all the stuff in the orbit of X, this is the same thing as the index of the stabilizer of X and the group action. This is an incredibly important theorem. Okay. So let's prove this is the length of an orbit. If you want to calculate the length of the orbit, all you have to do is compute the index of the stabilizer. This is most useful really when you're talking about finite groups, but it's true in general, and you'll see we'll set up a map here. Proof. If G acting on X equals H acting on X, where X is an A and G and H are in the group, then H inverse G well, in fact, when you write this, it's if and only because it's actually equivalent. Because the G operating on X is H operating on X, and that means that H inverse G operating on X is X, and it works the other way. And this is equivalent to saying right, that's equivalent to saying that H inverse G is in the stabilizer of X. Remember what G sub X is that's just all the crap that leaves X alone. And so H inverse G is one of these things that leaves X alone. And this is so, and of course, H inverse G is in this thing if and only if the left coset G of X is equal to the left coset H G of X. So in other words, what we glean out of this is if you have two elements of the group that leave something alone, then they give you the same left coset mod the stabilizer. So we now consider the function function F from left cosets of E to let me point out a couple of things. Now, F is well defined by argument above. These are all if and only ifs. And so if I have G Gx equal HGx, then I have G acting on X is H acting on X. So this is a well-defined function. And F is onto orb X, right? Because by definition, orb X is just X operated on everything in G. So if I want some particular G operated on by X, I just pick that left coset, right? So yeah, 1, but to this end, F like G of X, F H X. Then G operating on X. Which implies so that proves it. So what we've done is we've constructed this F projection between the elements of the orbit of X and these left cosets. Okay. Any questions? This is one of the coolest theorems, and this is we're going to have kind of a recurring theme with using this over and over again. Let me just admire this one more time. There we go. So, theorem 4111. So this is an important theorem. This is about a particular, this theorem concerns a particular action. But G and what I want to act on the set of left cosets of H. So this is our collection, our set that we want to act on. And what I want to do is I want to act on this by left multiplication. Let G act on A by or translation. Sometimes this is called translation. I've used both terminologies here. Let's try the associated permutation. Representative. Now, don't make too much out of this. What in the world do I mean by pi H? Pi H is basically our homomorphism that goes into the permutation representation. Y'all remember when I did that example with the 3 subgroups of S3, and I said, oh, okay, we look at the way it spins these things around, and that gives me my permutation. That's exactly what this pi H is. It's just this correspondence here. Number A, so here's G acts transitively on a set of these cosets. Number B, the stabilizer of the coset H is H itself. So what I'm saying is, let me put one H here. So this is a coset. The step that leaves the coset alone is precisely H. And C, general, the kernel of this action is the intersection of X, H, X inverse. So the kernel of this action is the intersection of every single conjugate of H. And this is the largest normal subgroup. Of G contained. We'll go through proof of this next time. Any questions on this? By the way, if, for example, you know something like G is simple, this will tell you a lot, because if H is a proper subgroup and G is simple, then this thing has to be identical. Okay, any questions? How about out there? Anybody got any questions?
I just wanted to ask something.
Okay,
Because
well, y'all take care and we will see you by Wednesday.